Thanks very much for the kind introduction, the opportunity to speak today. It's nice, these remote conferences, it's nice to see the names of so many old friends on the list, even if not faces and voices. So what I'm going to talk about today is probably not dissimilar to some of the concepts that you've heard already from Isabel and John, but I hope gives a slightly different slant, and is focused very particularly on chemistry being performed in the laboratory and the data that you can secure from that environment if you so choose to do so. So the first thing I wanted to do is just touch a little bit on the title of the sort of topic area today. We call this sort of dealing with data and tricks. And so a short internet search or dictionary search allows you to find that a tip is a small but useful piece of practical advice, which I think is probably what we're all looking for here today. But a trick actually is a cunning act or scheme intended to deceive or outwit someone. And of course, why would we choose to need to use a trick on the data that we are performing? And of course, I guess that becomes from a view that is not necessarily always widely accepted, but that we need tips and tricks because we have a tendency in our industry to shoddily collect a collection of somewhat slightly shoddy data. Shoddy isn't trying to impart particular blame, but it does infer badly made or done. So what I'm going to do is I'm going to give you a little introduction to DeepMatter and what we do, and then try and touch specifically on 3 tips in terms of the way that you might want to handle and use your chemical data coming out of the laboratory. Being a corporate organisation, please forgive me, this is going to have a little bit of element of advertorial about it, but I also tend to try and show you some examples, even if you chose to do this by a different means. So introduction to DeepMatter. DeepMatter is digitizing chemistry, and we are focused on improving the productivity of research and process chemists working within the laboratory and their colleagues, and also on their ability to discover new and novel molecules. And we do that by developing and commercializing products that combine laboratory hardware, and those are not just established laboratory hardware, but a bespoke proprietary sort of collection device, a Fitbit for chemistry, if you want to think about it like that, with state-of-the-art software enabled to improve productivity and predictability and speed for all sort of scientific outcomes. We span fields such as pharmaceutical research and development, not just industrial, but also academic work. We work in scientific publication and in teaching as well. Basically, anywhere where data really matters to improve or to demonstrate scientific outcome. And we have, I guess, 2 kind of core products which people are familiar with us for, albeit a range of cheminformatics products that we sell beyond that. The first of those is IC-Synth, a desktop machine learning-based synthesis design software for today's practicing chemists, retrosynthesis and forward reaction planning, or based on data collected either from scientific literature, so databases that you might have access to, or your own electronic lab notebooks. And digital glassware, a cloud-based software and hardware platform enabled to improve productivity in the laboratory itself. And that's what we're going to talk primarily about today by way of the examples that I'm going to give. So, digitizing chemistry, the tips, not the tricks. And the first thing I'm going to do is I'm going to encourage you to bin the old-fashioned write-up. And I want you to think about write first. And I'll explain a little bit about why I think that's the case a bit later. Secondly, I want you to think about collecting your data throughout the time course of a whole experiment. Don't just think about the endpoint of a reaction or of a piece of science. And finally, I want you to think about sharing your data in an easily and accessible and transferable format and the benefits that that brings, albeit it's not, not without challenges for different types of organizations. So, my first suggestion, first tip, is to bin the write-up and write first. And I like this picture. This is the Swedish chef from the Muppets, he personifies how I think some people think of chemists in the lab. Going in, chucking everything into a beaker, into a vial, into a reaction vessel, mixing it all up. And just waiting to see what happens. And the analogies between chemistry and cookery, I guess, have been made by lots of people on a number of occasions. But what we know is actually, even though people tend to write up their experiments after they do a reaction, they go into the lab with very specific intent. And that doesn't mean that you can't change what you do in the lab. It doesn't mean you can't adapt. But if you record your intent, this provides you with real strength when it comes to doing your retrospective data analysis. And so what I'm proposing you do before you go into your lab is you codify your chemistry. At DeepMatter, we codify our chemistry using digital glassware recipes. Recipes are not that different to a protocol, but they are easy to create, share, and recreate. We use them in the same way using sort of text prediction or just import from standard protocols that you might take from an electronic lab notebook, or you could just import directly from text from the scientific literature. And then we convert those into one of our recipes, which looks very much more like something that you might find in a master process record, perhaps as you go into process chemistry. But it provides for a really rich sort of plan when you go into the lab. That protocol is stored in the cloud. That means that you can access it from anywhere at any time by any of your colleagues. So you could access it here from home at the moment, and I'll encourage you later to go and have a look at our public data silo, and you can download a recipe. But you can also use the digital protocol as a basis for structured data collection in the lab, and I will talk about that in the next section. We went about this because we really wanted to bridge the gap from human inputted reaction information, which was done sort of post hoc, to provide machine readable procedures ultimately that can be used in chemical robotics and other environments. But I think it's really important to demonstrate that even if you're not going to use chemical robotics in the end, the ability to migrate from sketch and text, which tends to be the way I think about retrospective write-ups, to a readable and writable XML language is really, really powerful when you come to use things like machine learning and other sort of heavy-duty data analysis techniques. And back to the comments that John made earlier about the fact that the volume of data that is available to people now is significantly more than the knowledge that we would have had. I think it's important to be able to say that the tools that we have now need to be built and collecting data in a way that are accessible to these sort of bigger data analysis opportunities. The other thing that I think is really important about sort of writing first rather than writing up is the ability to provide intent and context when ultimately considering the outcomes of the experiment that you perform. The things that you will hear out on the road is that the fact that there's no repository of failed data. And the reason is that we provide scant regards to a failed reaction after doing an experiment. We write up in detail success, but history always sort of backs the winners rather than the losers. And I would encourage individuals to provide the intent and the context of the experiment that they were going to do, irrespective ultimately of whether the outcome is successful. And that means that when you then come to do your analysis, you have as good a repository of positive data as negative data. And that, I think, will lend itself to better prediction ultimately in the future, whichever algorithm you use to do your predictive chemistry. The stuff on the pictures on the right hand side here, just a demonstration of some of the capability that sits behind the digital glassware platform that we produce, but that's probably just for an aside. And just by way of an example, we've used our recipe environment to perform a range of different types of chemistry with our customer groups. This is a book called Hartwig coupling reaction. I'm pretty sure Roger Sale will have something to say about whether this is a commonly enough used reaction, but it is capricious. It is particularly capricious. And what we found is that by encouraging people to write their protocols first and then follow those protocols prescriptively, we find that the recipes, the yields vary significantly less between multiple different users in multiple different runs than if you just follow a paper protocol. And we think that's due to the amount of detail and the guidance. And we also found that better yields are typically observed when using a recipe. The recipe basically tightly improved the reproducibility. My second tip is that I want you to think about collecting data throughout the time course of the whole experiment. And I want you to collect it from not just one data feed, but from multiple data feeds. This is a picture of the Titanic when it was sinking. And the question is why did the Titanic sink? And I guess we can all speculate at length. But one of the theories is that the officer of the watch who was watching didn't see the iceberg due to an optical effect when looking out in front of them that meant that it wasn't distinguishable. Now, if you're not looking all the time and you're only assuming that one thing is the measure of success, then I think there is an opportunity for disaster in the chemical reactions that you might be performing. And so I think, again, what we've done with the platform that we've developed at DeepMatter and we're using is to follow arrays of data throughout the complete time course of the reaction. So not relying just on the endpoint, but on what happens while the reaction is proceeding. So we progress a run available from the lab either remotely, so you can do that from your desk at home if you control your chemicals or chemical reactions remotely, or in the lab itself using the tablet that you can see in the pictures on the right. We allow the users to provide observations and notes in real time to improve the richness of the data that is available to the users. And we encourage cloud access so that the data is available from not just yourself, but from others. And we collect multiple sources. So people will be aware that we have this sort of Fitbit for chemistry device, this device that collects a range of different data feeds, some which are familiar to chemists, so things like temperature and conductivity and so on, but also a range of data feeds that are perhaps slightly less familiar. So we collect video, sound, other slightly different pictures from within the round bottom flask. And we believe that by combining those data streams with perhaps the more traditional outcomes that chemists associate with their chemistry, so that might be an LCMS, an NMR, or those sort of traditional measures, then you get a much richer picture. And you're not reliant on any one sensor feed to determine what's going on in your reaction. And you've got the ability to not just understand what happened in your reactions, but actually intervene, take action, and change the course of your chemistry in real time. And I want to show that as we come on to an example here of a user reaction, which is IP protected, I'm afraid, so I can't show you what that is. But it's a bromination reaction. And when performed on multiple occasions, the reactions to the chemist visually looked to be proceeding well. They were boiling, they were refluxing as expected. But what you can see is one of those reactions proceeded really nicely and one didn't. And ultimately, we were able to identify through the streams of data feed and also from a bit of knowledge of the chemists that the failure of the reaction was due to a mislabeled solvent bottle. And the organic solvent that was being used obviously has a different boiling point temperature. So although visually, through one data feed, it was clear that the reaction looked like it was proceeding okay, actually, had you been following the alternative sensor streams, you would have been able to do something about it and change the outcome of the experiment, perhaps stopping it before it failed within 60 minutes and going on beyond that. Realize that we're coming close to the end, so I've got just one more tip that I want to touch on before we kind of hand over to any questions that might arise. But I want to encourage you to share your data in an easily accessible and transferable format. And I don't suppose there's anyone in the room that wouldn't disagree that there is value in data sharing. This is Otto von Bismarck, who said that fools learn from experience, and I prefer to learn from the experience of others. And clearly, you know, we are all capable of continuing to do experiments and record them ourselves, follow them ourselves, and learn from them ourselves. But actually, if we had access to a wider data repository of outcomes, both successful and unsuccessful, with confidence in the quality of that data, so that we could interrogate the outcomes of those experiments and the raw data themselves in an easily transferable way, then I think we can really start to learn, not just as individuals or individual organizations, but as a community. So, you know, at DeepMatter, data is our business. We are committed to open data standards, and we adhere to high standards of integrity and security. So, you know, whether you're a pharmaceutical company or an academic, you will still want to know that your data is secure, but that you can also share it with the people that you choose to share it with. And we would encourage organizations where there is the ability to share it more openly to do that. And we've got a strategy for doing that if you're interested in talking to us about it at some stage. But make sure you have access to your structured data stored in real time anywhere. And as organizations, particularly in this, you know, sort of post-COVID environment or current COVID environment, I guess as we would call it, you know, there is less travel, there is less ability to share data so easily and so transferably. We think that cloud will ultimately drive further use of data sharing. We want to make sure that you place your data to the extent you can in one place, and so that you can access it easily and in a comprehensive environment. And you want to be able to download it and share it with your colleagues so that they can easily interrogate it. And so I think those are things that we would encourage you to do. And the aggregated structured data sets will improve real-time and post-run analytics. And all of this, you know, leads to improved insights for better productivity and discovery. So I just want to show you one last example of where we felt there was a great outcome here. So some synthesis of this molecule, Michael edition, originally reported in Organic Synthesis. We did a small round robin, looking at different scientists in different labs using the same recipes. And interestingly, you know, it wasn't the endpoint data that ultimately dictated the success of the reaction. It was the time course data. And despite the fact these were done in different parts of the world, different parts of with different scientists in different labs, we found that, you know, their ability to share that data allowed them to correlate together and ultimately identify routes to increase the yields by essentially the different addition of rate of reaction of the solvent. So I think I've had my 20 minutes. So in summary, you know, human interaction to produce chemical products introduces many opportunities forever, whether that's 50% of science being irreproducible, as per John's comments earlier, are a stretch. I think it's fair to say that there is irreproducible chemistry because the data that is provided in as complete a manner as anyone might have historically chosen to write it down. You know, there are challenges in terms of the barriers of peer review. there are the prevailing environmental conditions that ultimately make a difference. And finally, we don't have that access to a big repository of data outcomes that are both negative as well as positive. But we think that if you chose to take an approach which involved binning the write-up and writing first, so that you've got a set of contextualized information before you go into the lab, collect the data through the time course of the experiment, not just at the endpoints, so that you can understand not just whether failure or success has occurred, but when it has occurred, and then to share those outcomes in an easily and accessible and transferable format with your colleagues through the web. Then you've got really the ability not just to fail it, but to nail it. And our digital glassware platform is designed to help improve that productivity and discovery in those labs. And finally, what's the worst thing that could happen? Well, of course, you could be a Nobel Prize winner and find that you have to retract your publication from Science. I guess that's probably about the worst thing that could happen to you. But I would encourage you, you can avoid that. Check out some of our sample data at the link here, public.deepmatter.tech. And, why not have a go with our free download of the digital glassware platform. And with that, I think I'm going to wind up.